Welcome to the bleeding edge of kernel development. Today, we are deep diving into SCHEDX, or SCX, the Linux kernel feature that enables implementing task schedulers using BPF. For infrastructure engineers managing hyperscale clusters, the ability to tailor CPU scheduling to specific workloads, like gaming or massive database shards, is revolutionary. However, moving scheduling logic into BPF programs introduces a black box problem. Traditional tools like TOP or perf often struggle to capture the granular, millisecond-level decisions occurring inside a custom SCX scheduler. We need a way to inspect internal states without crashing the production kernel. That is where the SCHEDX dump Tracepoint becomes our most powerful diagnostic tool. By the end of this session, you will understand how to leverage this tracepoint to debug complex scheduling behaviors in real time, ensuring your ultra-scalable systems remain responsive and efficient even under extreme load. If a high-availability system experiences jitter or unexpected latency spikes, your first instinct is to check CPU utilization. But in a SCHEDX environment, high CPU utilization doesn't tell the whole story. You might see 95% load, but is that load balanced? Are tasks being starved by a logic error in your BPF maps? Traditional tools cannot see the internal priority queues or the dispatch versus consume logic defined in your custom code. This lack of visibility is a major risk for senior architects. Without deep introspection, a minor bug in a BPF scheduler could cause a global outage across your infrastructure. We need to peek inside the scheduler's brain while it is making decisions for thousands of threads per second. This is precisely why the SCHEDX dump tracepoint was engineered, to provide a high-fidelity snapshot of the scheduler's internal state on demand. The SCHEDX dump tracepoint is not a typical logging function. It is a high-performance hook designed to dump the entire state of the SCX scheduler when triggered. Think of it as a core dump specifically for your scheduling logic. When a task fails to schedule or a watchdog timer expires, the kernel can trigger this tracepoint to output structured data. This data includes the state of every CPU, the tasks currently in the dispatch queues, and the values of your BPF maps at that exact microsecond. For architects, this means you no longer have to guess why a P99 latency spike occurred at 3 a.m. You can analyze the dump to see that, for instance, CPU 42 was holding a lock, while 500 tasks were queued in a specific BPF ring buffer. This level of detail is essential for maintaining high availability patterns in distributed systems. To use the SCHEDX dump tracepoint, you must be comfortable with the Linux tracing subsystem. Generally, this involves interacting with the tracefs file system, or using front-end tools like bptrace or tracecommand. To enable the dump, you navigate to the events directory and write 1 to the enable file for SCHEDX:/SCHEDX dump. However, because the data volume can be massive, often several megabytes per dump, you must use filters. For example, you might only trigger a dump when a task's wait time exceeds 100 milliseconds. This surgical approach prevents the tracing system from overwhelming the very CPUs you are trying to monitor. In ultra-scalable systems, the observer effect is real. If your debugging tool consumes 20% of your CPU, your data is compromised. Precise filtering ensures you get the facts without the overhead. What does a SCHEDX dump actually look like? It is typically presented as a series of structured key-value pairs, or a JSON-like format, depending on your user space tool. Key fields include the SCX status, which tells you if the scheduler is active or in a transition state, and CPU data, which provides a per-core breakdown. You will see fields like runnable tasks, running task PID, and dispatch queuing. If you see a dispatch queuing of 150 on CPU 5, but 0 on all others, you have discovered a load balancing failure. Furthermore, the dump includes metadata about BPF map usage. If a hash map representing your priority levels is full, the dump will reflect that overflow. For a senior engineer, these numbers are the DNA of the system's performance at a single moment in time. One of the most insidious issues in custom scheduling is task starvation. This happens when your BPF logic accidentally overlooks a specific class of tasks, leaving them in the queue indefinitely. By analyzing the SCHEDX dump, you can correlate task IDs with their wait times. If you notice a task with PID 8902 has been in the runnable state for 5,000 milliseconds without being dispatched, the dump will reveal exactly where it is stuck. Is it in a global FIFO queue? Is it pinned to a CPU that is currently running a high-priority interrupt? The dump provides the where and the why. In a global scale architecture, identifying these zombie tasks early is the difference between a smooth user experience and a cascading timeout failure across your microservices. SCED-X heavily relies on BPF maps for state management. However, at high core counts, say a 128-core EPYC processor, lock contention on these maps can become a bottleneck. The SCED-X_dump tracepoint helps visualize this contention by showing the time spent waiting for map updates. If your dump shows that multiple CPUs are frequently blocked while trying to update a single global task stats map, you have identified a scalability ceiling. The solution might be to move to per CPU maps or to use lockless data structures. This insight is purely architectural. You aren't just fixing a bug, you are redesigning the data flow to support higher throughput. The Tracepoint provides the empirical evidence needed to justify such a significant refactor to stakeholders.
While raw Tracepoint data is invaluable, it can be overwhelming. This is why tools like SCX Stats are essential. SCX Stats is a user space utility that consumes the SCED-X dump tracepoint and converts it into a human-readable dashboard. It provides real-time histograms of task latency, dispatch rates, and migration counts. For a senior infrastructure engineer, this dashboard is the cockpit. You can see that your custom scheduler is performing 10,000 migrations per second, perhaps too many, and adjust your BPF code's migration cost threshold accordingly. By integrating Tracepoint data into your CI/CD pipeline, you can even catch scheduling regressions before they reach production. Automated scripts can trigger a dump during load tests, compare it against a baseline, and flag any deviations in dispatch queue behavior.
Let's look at a real-world scenario. A large cloud provider noticed that every 60 seconds, one CPU core would stall for 200 milliseconds, causing a ripple effect across their K8s cluster. Standard logs showed nothing. By enabling the SCED-X dump tracepoint with a 60-second trigger, they captured the state during the stall. The dump revealed that a periodic BPF garbage collection task was accidentally locking the entire scheduler state to clean up old session data. The evidence was undeniable. SCX status was locked, and CPU 0 was the owner. Without the dump, identifying this sub-second lock contention would have taken weeks of trial and error. With the tracepoint, the fix, a lockless GC implementation, was deployed in hours. This illustrates the power of high-fidelity observability in mission-critical environments. As we conclude, remember that SCED-X and the SCED-X dump tracepoint represent a fundamental shift in how we manage compute resources. We are moving away from one-size-fits-all scheduling toward highly specialized, workload-aware policies. As senior architects, your ability to debug these custom schedulers is just as important as your ability to write them. Master the tracepoint, learn to read the dump output, and use tools like SCX Stats to visualize the invisible. By doing so, you ensure that your infrastructure is not only scalable, but also resilient and transparent. The journey into BPF-based scheduling is just beginning. Stay curious, keep measuring, and use the data to build the next generation of high-availability systems. Thank you for joining this deep dive into kernel observability.